So when you think about physics, what comes to mind? Probably black holes, maybe quantum particles, right? But behind all of those massive ideas, there's a simple secret. And that secret is math. But it's not just about crunching numbers. It's literally the language the universe is written in. So in the next few minutes, we're going to build a physicist toolkit together with all the essential math you need to start decoding how everything works.
So let me ask you this. What does a planet's orbit have in common with a ball you just threw? I know, it sounds like a trick question, but the answer is, well, pretty much everything. The exact same mathematical rules describe both of those paths. And that, right there, is the power of physics. It all starts with just a few fundamental tools.
Okay, so let's open up our toolkit. First up, the graph. Honestly, it is the best way to see how one thing affects another. When you plot data, you turn this boring list of numbers into a clear, visual story about how two different things, like, say, distance and gravity or force and acceleration, are connected to each other.
And really, when you boil it all down, these relationships come in two main flavors. On the left, you've got a direct relationship. The more force you put on something, the faster it accelerates. Simple. But on the right, you have an inverse one. The farther you get from a star, the weaker its gravity gets. So much of physics, so much, just comes down to one of these two patterns. One thing goes up, the other goes up. Or one goes up and the other goes down.
So if a graph tells a story, then the slope is the plot twist. It tells us just how fast that relationship is changing. You've probably heard it called rise over run. It's just, for every step you take sideways, how many steps do you go up or down? A really steep slope means a big, dramatic change, while a shallow one is more slow and gradual.
And you're really only ever going to see four types of slope. It can be positive, heading uphill, like you're climbing a mountain. It can be negative, going downhill. It can be zero, totally flat. Or, in this one weird case, it can be undefined. That's a straight vertical line. It's like trying to divide by zero, which, as you know, is a big no-no.
All right, so we've got our first tool down. Tool number 2 is all about measuring the physical world around us. For that, we need the basic formulas for shapes and the space that they take up.
Think of this as your cheat sheet for the universe's basic building blocks. You want to calculate the pressure on a surface or the volume of a whole planet. You're going to need these. Now, don't worry about memorizing them all right now. Just know that with these formulas, you have the vocabulary to measure almost any object you can possibly imagine.
Our third tool deals with something that might seem a little abstract, but it's incredibly predictable: angles. See, whenever lines cross or forces get applied, angles follow a super strict set of rules. And once you know these rules, you can solve all kinds of geometric puzzles.
And here are the most important ones. When two lines cross, the angles opposite each other are always identical. Always. And when you have a line cutting across two parallel lines, kind of like a ray of light passing through a lens, you get this perfect, beautiful symmetry. Corresponding angles match up, and the alternate interior angles, the ones that make that little Z shape, they're also exact copies of each other.
Now, this brings us to what I like to call the magic number in geometry: 180 degrees. Any angles that add up to 180 are called supplementary, and trust me, you find them everywhere. So where do you spot them? Well, they're on any straight line. You'll find them between parallel lines on the same side of that crossing line, and here's the big one: the three angles inside any triangle you can possibly draw. I don't care what it looks like. Will always add up to exactly 180 degrees. That's just a fundamental rule of how our universe is built.
Okay, this is where it all comes together. We're about to combine these ideas with our master tool. I'm talking about the right triangle. It is one of the most powerful shapes in all of physics and engineering, period. It's the key to measuring things you could never possibly reach, like the distance to a star or the height of a mountain.
Come on, you've definitely seen this one before, right? The Pythagorean theorem. It's famous for a reason. If you've got a right triangle and you know the lengths of any two sides, this simple, elegant formula will give you the third. It's been a cornerstone of math for more than 2,000 years.
But there's a catch. What do you do if you only know one side? Let's say you know how tall a building is, but you can't measure how far away you are, or the diagonal distance to the top. Well, now the Pythagorean theorem can't help you. We need something else. We need another tool.
And that tool has a kind of funny name: SOHCAHTOA. Now, it's not some complicated equation. It's just a really simple way to remember the three basic functions of trigonometry: sine, cosine, and tangent. And if you have just one side and one angle of a right triangle, this little word is the key that unlocks everything else.
Let's break it down real quick.
Saw means sine is the side opposite the angle divided by the hypotenuse. Ca means cosine is the adjacent side over the hypotenuse. And toa means tangent is the opposite side over the adjacent side. That's it. Those three simple ratios are all you need.
All right, enough theory. Let's see this thing in action. Here's a classic physics problem. You've got a truck bed that's 1 meter off the ground. A ramp going up to it makes a 40-degree angle with the ground. The question is, how long is the ramp?
So how do we tackle this? First things first, let's identify what we know. The 1 meter height is opposite the 40-degree angle, and the ramp itself, the thing we want to find, is the hypotenuse. Opposite and hypotenuse? That's so, from SOHCAHTOA, so we know we need to use the sine function. Then we just rearrange the formula a little bit to solve for h, our hypotenuse.
You pop that into your calculator and boom, there's your answer, 1.56 meters. And that makes sense, right? The hypotenuse is always the longest side of a right triangle, so we knew our answer had to be bigger than 1 meter. It's a great way to do a quick gut check to see if you're on the right track.
Okay, let's try one more. This time, we're going to work backward. We have a triangle, and we know two sides. The side opposite our mystery angle is 3, and the side adjacent to it is 4. Now the challenge is to find the angle itself.
So, same process as before. We identify our sides, opposite and adjacent. We look at SOHCAHTOA, and that points us straight to TOA, which is tangent. But since we're solving for the angle this time, not a side, we have to use the inverse tangent function on our calculator. It usually looks like tan with a little -1 next to it.
We plug in our numbers, the inverse tangent of 3 divided by 4, and just like that, we get our angle, 36.9 degrees. We just found a missing angle using only the lengths of 2 sides. Pretty cool, right?
So, let's recap the awesome toolkit we just built. We started with graphs so we can describe relationships. Then we added formulas to measure space and shapes. We learned the unwritten rules of angles to understand how systems behave. And finally, we used triangles, our master tool, to solve for things we can't see or reach.
Look, these aren't just some abstract math ideas. They are the actual instruments you use to measure everything, from a simple little ramp to the massive arc of a planet. Remember that orbit we talked about at the beginning? It's just a big puzzle of graphs, angles, and triangles, and you can solve it with the exact same tools we use today. You now have the fundamental toolkit of a physicist. So the only question left is, what are you going to measure first?